Okay. Okay, so I think I will finish off torsion and add one more part just for the last sections. That will be the equilibrium of beams. Basically, it is going to be a system of equations in beams, and basically what we need to do is to evaluate the internal forces and bending moment. Okay, but I think I will just finish off the torsion and then move on to the equilibrium of beams. And by the way, our schedule is tomorrow's quiz, right? But I think since this is already 20th of May, I would like to suggest when is our final will be? 3rd of June?
You want to have on the school schedule?
Yeah, I think 3rd of June, right?
Yeah, 3rd of June.
3rd of June. So if 3rd of June was our finals, how about these 2 days, today and tomorrow, I will continue first finishing off all the contents. 27 and will be the review, 28 will be quiz, and 3rd of June will be finals. And there will be one more content just for your exercise, practice and exercise. I will add practice and exercise within this week or next week. At least maybe 1 or 2 videos. One is for chapter 4, the torsion, and the other one will for the equilibrium of beams. And then that's it for the preparation for the course. So today and tomorrow, I think I will continue to finish off all the contents. So today I will finish off the torsion, introduce you to the equilibrium of beams, and finish off the beams tomorrow. And then 27, give you some overview of all the contents. 28 will be the quiz for chapter 3. Okay. So again, chapter 3 quiz will be 28. Okay. So today and tomorrow I will finish off all the contents. 27 we can have a review. 28 your quiz, and June 3rd will be final exam. There will be in between additional contents. I will prepare some practice and exercise, especially for chapter 4, the torsion and equilibrium of beams. Okay. So I will just maybe finish off the torsion for today's class. So last time we have the introduction to the statically indeterminate for the torsion, and basically it will be very similar approach for the torsion and axial deformation. They are going to be very similar. So if we look at this basic force method, this also similar. So what you need to do is you need to find the equilibrium, and then finding the torque twist equations, or in the chapter 3 we say the elongations, this axial deformation, and then add the compatibility equations. Okay, and then solve these two system of equation to get the torques, and then solve the problem. Okay, and there is one example here which we can see. I think I will try my best. It's not too long. So for example, here we have the steel shaft with some shear modulus and also a radius r. It's on, the unit is American unit, so it's in inch and pounds. So you have length, you have the alloy tube, aluminum alloy. So you have steel in the inside and then aluminum in the outside layer. And then you have external torque, which is 5,000 pounds-inch, applied at the node B. So you twist the joint B, and then we need to find the maximum shear stress in steel and maximum shear stress in aluminum. So we have two different questions. So first is the steel, and the second is the aluminum. So we can break down this two shaft, the aluminum and steel, based on the joint. So we have A, B, and C. Okay, we can slice become at least 3 or perhaps 5. So A, and then between AB, B, BC, and C. Okay. So at A, we have some reaction force because they are both attached to the wall. Okay, they attach to the wall. So maybe we start from the middle one. So we have the torque, external torque TB. So we may have reaction forces T1 and T2, and also maybe also if we look on before we start to cut, we already see that when we applied, so we start by applying this TB. Because we applied TB, there will be reaction force in A and C, which is counter the torque at B, right? And then we slice. We slice and makes each one of them a diagram. So from this TA, we need to cancel TA by adding T1, okay? And then in the element 1, we need to add T1 as opposed to the other T1 as so that they will cancel out, right? So we have another T1. So it's like making a pattern. So we start from here, from the picture above. We need to cancel the TA on this node A by taking this T1. But we need to cancel this T1 in another diagram, which is this one here, right? So we have this, and then we need to also cancel this with another T1 because they are in one element. Okay? So we have another T1. They have the same value but different rotations. They need to be cancelled out, right? And then we have another cancelling out since this is the same element. So this is another T1. So this is to help us to have a equilibrium in each part. Okay? So we have equilibrium for TA and T1. The equilibrium for this is on the T1. This is T1. TB and T2, and we can have another one as we can see from the other element as well. So we can write the node. So for each node, we can have expressions. Let me add here. Okay, so let me write for node A. We can write that this is okay, standard. So we say that right-hand rule. So every time we take this, and this becomes our default by system. So this is the positive one. The one that counter this will be negative. Okay. So TA will be positive, and T1 will be negative. So TA minus T1 is 0. Okay. And then for B, we have TB positive, T1 positive, and then T2 and T3 is negative, right? So TB plus T1 minus T2 minus T3 equals 0. If you define different convention, as long as you're consistent, it should be okay. But I think we can set the right-hand rule as our positive sign. And also, if you maybe not making the correct equilibriums, then the whole process after the following process will be incorrect. Okay, so you need to make sure that all the rotation is in the correct positions. Okay. Then in C, we can make the other one. So we see TC, positive, all positive, right? TC, T3, T2, it's all positive. So if we just take a look at joint B, because they have all the components, that is important, 1, 2, 3, and TB. So we have TB is equal negative T1 plus T2 plus T3. Okay. And then we can apply the twist angle, which is the TL and then GI. T is for torque, L is for length, G is for the modulus, and I is for the inertia. Inertia is basically because it is having the tube, it's always a pi over 2, and then multiply the radius squared, or using diameter. Also, you can compute. So perhaps we can say that for every part of it, we can compute the inertia. We can compute inertia for steel. Or if we look at this element 1 and element 2, they are the same, right? There's the steel. So we can say element 1, the inertia will be the same. And they have the same length, and diameter is also the same. So pi over 2, diameter is 10 or 1 inch, sorry, with power of 4. And we can compute this, and this is the result. And the last one will be the aluminum. This is the tubular or hollow shaft. So we have pi over 2, and then we have the differences in the diameter with power of 4. This will be around this. Okay. We can compute for example, if we let the L over GI, this will be, let's say, the small f. We can also compute because we know all the numbers, right? Or if you prefer to compute in a one big equation, it's okay. But I will prefer compute one by one and then later substitute. Okay. So we can substitute for f. Let's say this is for f1. This is L, G, and I, P for element 1. So L for element 1 is 30 inch. I think this is element 1, this is element 3. So 30 inch. And then the modulus is 11.5 psi. And then multiply with the inertia is 1.71 inch with power of 4. And this will be the result. Radians over pounds inch. And do the same thing for the element 2. This will be 20 inch. Oh, wait, this is not 30, 10 inch. This is the same. Okay, this is also similar, but now it's aluminum. So we use the modulus for aluminum and the inertia for aluminum. Okay, so we have all this F, and then we have the geometric for the deformations here. So based on the picture, let me write with the red color. So we have a twist angle for element 1. If we look at how it goes for the whole relative twist angles, if we look at the element 1, so suppose that we have the twist angle for 1. Okay, so the twist angle, since we have the TA and TB, then if we take relative, suppose that this is twist angle A minus twist angle B, okay? And then since the twist angle A is attached to the wall, then the A, this twist angle will be 0. So let me write here that the twist angle 1, let me write all the possible twist angles. So twist angle for element 2, that is in between B and C, this will be, if taken this positive for B, then we need to minus the C, okay? Because they have the same direction. So the T2 should be the differences between this B and C. And the same thing with the twist angle 3. Should be the same with 2 because they have this in the same length, in the same interval. So this is also the same with that, okay? And then we can write the that this is going to be 0. This is also 0. This is also 0. So we can write that this is going to be that, and so the twist angle 1 is negative twist angle 2. Also the twist angle 3 is the same with the twist angle 2. And we are going to use this to compute our equations. Okay, now because we have this and we know that the twist angle is based on this, so we can write here the twist angle 1 is T1 F1, right? Twist angle 2 is T2 F2. Okay. And twist angle 3 is T3 F3. And then write up all the connections between the twist angle. So we can exchange and then taken into the calculations, we can compute the T1, T2, and T3. So let's substitute. So substituting, let me write this around to the left. So we can write F1 T1 is negative T2 F2. And then F1 F3 T3 is T2 F2. Okay. Or maybe to make it similar, maybe write F2 T2 F2 T2. Okay, and then we can solve this simultaneously. So we get that the TB is this, right? This one here. Let me write up the TB. TB is negative T1 plus T2 plus T3. Okay. So we can exchange based on this TB. So for example, we could start by taking this T1 is basically negative TB plus T2 plus T3, right? So we can get for T2 for exchanging this T1, or we can get T2 if you want to make it T2 TB plus T1 minus T3. Okay, anyway, we can write this as F1. Then suppose that we want to solve for T2. So this will be negative TB plus T2 plus T3. And we have this is F2 T2, okay. And then we have same here, T3 is F2 T2. We can exchange all with 2, right? So we can exchange T3 for F2 T2 over small f like that. So for example, we can write this is negative TB plus T2 plus T3 equal negative F2 T2 over F1, and then exchange the T3 with another part of it. So this will be negative TB plus T2 plus F2 T2 over F3. But basically, you're going to solve the equations. Well, you could always take the equation with the calculation for each one of the F1, the small F1 here. Well, I would like to just solve the equation first. So this will be T2 1 plus F2 over F3. This is negative F2 over F1 T2. Oh, I think I need to, let's say we multiply with F1 F3. So this will be negative F1 F3 TB plus F1 F3 T2 plus F1 F2 T2 equal negative F2 F3 T2. And then we move the T2, will be F1 F3 plus F1 F2 plus F2 F3. Then we have F1 F3 TB. So T2 is F1, F3, TB divided by this whole thing. Okay. And based on this T2, later with the same reasonings, you can have the T1 and T3. So we are going to get T1 is negative 2284. T2 is 1142. And T3 is, okay. So we get T. And then we have the tau max. That is the questions, right? So I think I need to make this a little bit going here and make it resize a little bit. And all this stuff I will pull and write over here, make it resize a little bit. Okay, and then from the results we have the tau max for steel. This is Q1. We need to only the value, so we take the absolute value, radius, and then the inertia. Inertia we have done, right? Radius we have, and T1 we already have. So 2284, 1 inch divided by 1.57, 1 inch with power of 4. Oh, I forgot. Should be pounds and inch. And this will be 1454 psi. And tau max for aluminum. Aluminum is only for T3. And similarly, we have taken all the information from the previous calculations. This will be 369.9 psi. So this is the tau max for each one of them. So steel and aluminum. But I think the most tedious part is solving these equations. Okay. And this is a typical statically indeterminate problems in the torsion. Okay. Okay, I think that's for the basic force method. One method, just to conclusion on this part here. The other part is the displacement method, but I hope whether it's basic force or displacement method, the difference is the system of equation that we are going to apply. But the principle or the ideal formulations, they are going to be the same, they're going to be similar, but the way we used our equations, for example here, for displacement method, we are going to have a system of equation for the torque. The previous one, we have the system of equation for the twist angle, right? Which they are going to be from the same formulations, right? From the idea is from here depends on which part that you are going to apply. So we can apply this as like that, and then we can say we have K, which is going to be this K. The previous one we have the F, right? We have this, but basically they work very similar. So to make it clear, let's go for just a like example. Maybe I will write example here. So suppose that we have a steel shaft, we have the modulus, and we have the radius, we have the length, and then we have the outer radius as well. So the aluminum, it has a hollow structure, and we need to determine the angle of rotation at the A, and then maximum shear stress in the steel core, and maximum shear stress in the aluminum shaft. So it's similar questions. So we can, first of all, since this is going to be from point A to B, all the elements, they are going to be the same. So the element will be based on, suppose that we have steel and aluminum. Let's say the aluminum or the steel is 1 and aluminum is 2. Okay, and suppose at the point A we have this torque A that is going to be applied at 350 Newton meter. So it's applied at the torque at the joint or the node A. So we have torque A, and since both 1 and 2, they are in one piece element, so they are going to be counter the external torque. So T1 and T2, they will counter the TA. So we have TA will be equal to T1 plus T2. So this is the equilibrium. We start by equilibrium at A, and then we could apply directly that T is basically this one, okay, the twist angle, and then GIP over L. I can write this with another name, small k, like that, and we can basically for element 1 and element 2. So for steel, we can have the inertia. So pi over 2 is 25 millimeter, and then with power of 4, and then we compute, and this will be the result. And then for aluminum, we have hollow. The outer radius is 37.5. Okay, so 37.5 minus 25. Okay, and this will be 2493. Okay, we have 2 inertia, and then we can compute this small k. K1 is, you can write 1. So G for steel is 78 GPa. GPa is basically with power of 9 multiply with or if you want to make it the same, maybe this is 6 and this is millimeter squared. And we have 95.72 per radians. And do the same thing for the aluminum. the same length, and then inertia. And compute. Okay, since these two elements, they are on the same same one piece of the shape, then the angle, they are going to be the same angle. So the deformation, we can write here. So geometry of deformation. 1 and 2 will be, the twist angle will be the same. Will be basically the difference between the twist on A minus the twist on B. So since the twist on B will be 0 because it is attached to the wall, then the twist 1 is equal to twist A, twist 2 also the same. So I think we can have a direct answer after we solve the solutions for the torque. So from the displacement equations, we have the T1 or force equation is K1 twist A, T2 also the same, which we can refer to our equilibrium at the beginning. T1 plus T2 is equal TA. So the twist A, K1 plus K2 equal TA. And since we have compute the K, so we can write the twist angle A as TA divided by K1 plus K2. So we can input these two. So this is K1, this is K2, and TA is 350 Newton meter. So we can input all these conditions to get 1.4 with power negative 3 radians. So this is the twist angle at A. And then the maximum shear stress for steel and for aluminum. So since we know that the tau max for steel, this will be T1 and the radius 1 divided by the inertia for steel. We can input all the all this stuff here. Well, but before that, we need to compute the T1. So we have twist angle A is this, so T1 will be K1 twist angle A. This will be equal to 142.37 Newton meter. And we get also T2, which is 207.63 Newton meter. Okay, based on this T1 and T2, we can compute the tau max. So this is going to be 5.801 megapascal, and tau max for the aluminum will be T2, R2, only the outer radius. Okay, remember. If you have the hollow, tube, the tau max will be on the radius, the outer surface radius. Okay. This will be 3.123 MPa. Okay, so that's the answer for tau max. And again, this will be a typical questions in the statically indeterminate. Okay, so yeah, I think that's it for the statical indeterminate structure. I have one more example here, but I don't think we have time for this, but this will be very, it can be as complicated as this one. So you have a gear like this, and then you can compute the torque, and because it will connect all the gear and the shaft, so you will have this kind of like a free diagram like this. Okay, but I don't think I will give you this kind of questions in the exam. It takes too long to be computed, but the idea is still the same. Okay, the idea is still the same. And also I skip the power shaft, which is relations between the torque and the watts or the power. So you have power and you have the angular velocity, but I will skip that part also. So then the next part on our chapter, which is the final chapter in this course, is the beams, the equilibrium of beams. As I mentioned at the beginning of the course today, we are going to complete this equilibrium of beams, hopefully within 2 days, and give you additional videos. I will prepare a video for exercise, especially for chapter torsion and beams. Okay, so let me start with the beams. Okay, so what we are expecting to solve, or what we are expecting to learn in equilibrium of beams is basically, since we have some differences, basically, for example, here we have different kind of beams with some, they are distribution load and they are simple load. We have some a beam called cantilever beam, which is the fixed end. So this is fixed end, so it's cantilever. Or we have the supported beam, which is we have this pin support. This is a pin support here. And of course, we have learned how do we apply our statics and mechanics, especially when we analyze the equilibrium, right? The equilibrium. We have also the roller. For example, here's the roller support. And basically we can combine and we can play around with it, right? So there are several type of beam. It can be cantilever, it can be prop cantilever, it can be simply supported beam with distributed load, or a continuous beam. Okay, so this is 4 types of beam. And basically, if we learn about beams, we learn about loads, and there are many loads. We have the distributed, let's say transverse loads. We have concentrated loads, or transverse force, or we have a couples that we can illustrate with a moment. And if we look on the example on how we could analyze, we can look at this picture. So this is a shuffle. Imagine that you are working with the shuffle. So you have a weight with those dirts, or you have a soil, and then if we analyze the length of the shuffle, it's L. And suppose that between your hands we have the distance A. Okay. So the reaction force, because of the weight, then we are going to have at B, the reaction force will be equal with the weight and your reaction force at A. Okay. And of course, using the moment, if we take this equal to 0, let's say this is going to be on the perspective of A. So we have the, let's say this one is positive. So WL and then minus RBA will be 0. Okay, we are going to continue later. Okay, let's continue. Okay, so what we are doing now is we are going to see if we move our hands with some cases, okay, some scenario that might be possible, and you could also try this maybe if you have like a long it's not. Well, you could always try with other equipments, like for example, mops or brushes, or perhaps something that's quite long. If you take that and you hold your hands like this, and you can move your hands. For example, you can move your left hands like this one. You can move this closer to your back hand. You'll feel more heavy, right? You'll feel more heavy because of the length, and then the moment will be greater, right? So for example here, because we have now devised this reaction force between these all the points, and using these equilibriums, we can set, for example, if we make the let A is closer to L. Okay. For example, here is our A. So we make this A closer to L, which means the RA, or here, the RA here, which we have. So if A is getting closer to L, this will be 0, right? So this will be 0, and the load will be, we can feel the loads at the reaction force B, okay? Which means that the if we multiply the reaction force with A, this is equal to WL, okay, the whole length, and this will be a constant. And the hand at B, it will be directly under load with this W, right, load W. But if we make the A, so if we make the A equal to 0, so the A is equal to 0, which means that this is going to the left, okay, then our RA, this will be L divided by 0, which is infinity, so this will be infinity, and RB also the same. And you have the WL, which is constant, and which is going to be very, very large, right? So that's if we observe the difference when we move our hands, okay? So then the third part, we can try to cut and slice some of the components. For example, here, since we have the A, B, C, our points, then we slice at B. We slice at B. Then we have the internal forces that we call it internal forces. We have the shear force, which is V. And then we have all the forces that is going to be to cancel each one of another. And then we have the so let me write here. So we have the V, which is transverse shear force. So this needs to be equal to W of magnitude W required to satisfy. And then since we have here, we have internal force, and there will be no net horizontal force on the cross sections, and then no external loads for the horizontal part on each one of the free body. Okay, so we can let the C that need to be equal to T. So this will be the tension and compression. Okay, so this is tension and compress. So C should be T, and then we have the bending moment M, which is the couple of the W, L minus A. Okay. And with moment arm, let's say B, that is less than L, then all the C equal T, this will be equal to W, L minus A over B. So we need to have a compressive and tensile normal stress, which is the same magnitude with the C and T, that need to be greater than W. Okay, let me get into the let me go up here. Okay, if we have W supposed to be 12 pounds, L is 50 inch, and A is 10 inch, B is 1 inch. And if we compute using the same equilibrium as the previous one here, then we get the RA the reaction force will be 48 pounds. Reaction for B is 60 pounds. And then C equal T, using the WL minus A over B, this will be equal to 540 pounds. So using the numbers here, we could see that the worker, or only a few workers that can hold the shovel if you have A less than 10 inch, okay? Because it's going to be pretty heavy, right? So if A change to 5 inch, which means here we are reducing the number. As we can imagine, it will be going to be very heavy. RB will be 120 pounds. It's twice as much and CT will be, oh, sorry, this should be 480. This should be 540. So it will be very, very heavy. Okay. So conclusion is it's getting heavier when we change, when reducing the size A, reducing A. Okay, now let's consider we have the transverse shear force and bending moment. At the cross section at C. Okay, suppose this is the C here. So let me move to the next slide here, just to show you what we might expect. So we need to have VC, which is transverse shear force, and then MC, which is the bending moment. At C, cross section C. Okay, VC and MC must act to maintain the equilibrium. And then we have the internal stress resultant. This is internal stress resultant. As we see from the definitions, the shear force is negative integrations with respect to A, tau xy of the coordinate xy dA, and M is negative integration with respect to A, y sigma x of xy dA. Okay, so what is this? This is basically we take the small part from the elements. We take the small part and we say that the tau is on the it will be orthogonal to the x-axis or to the plane, and then using that sigma or the normal force or the normal stress with the distance between the center of the mass and the origin, which is y, that will be the definitions for the moment, right? I think we have done this at the early chapter 2. But the idea here, we could have these two shear force and bending moment all together. Okay, so for example, if we cut here, we have the shear forces and the bending moment. Okay, and if we look from the side, we could have we call this as the positive V and M if we cut this section X. Okay, so every time you have this, we need to draw in symmetrical. Okay, so if you have the left is going down, the right will be going up, and this will be by default, this will be the positive, and the positive V and M on the section X. Okay, and if we look on the sign conventions, for example, if we have the suppose like this one here, we call this is the first one is positive shear. Okay, positive shear, And then we have the positive moment. So when we bend inwards and it's become concave. So beam, or let me write here, concave beam means that we apply bending moment as like this one, okay? Like we make it like that. So when you have bending moment that is going outwards like this, it will be downwards like that. It will be negative. It will be concave downward. Okay? And this is the sign convention, and you need to remember how to take it by default. Okay. Okay, I think I will go for just one example to see what we are expecting. So equilibrium in beams, we are going to see the observations on the shear force and the bending moment. What will be graphically will be displayed, and how we can make those graphics from the free body diagram. Okay. So let's move to our first example here. So suppose that we have the cantilever beam like this. It has a concentrated force at C and a couple of 4 kilonewton at D. And we need to determine the shear force at B and bending moment at B. So of course, this is forcing us to cut this, right? So we cut this at point B. So when we cut B, suppose that we have this. So what we need to find is and remember, when we cut the right part of the elements, this is the positive side. Okay. So this is always like this. If you cut and take the left part, VB going down and then moment going up. But for the right part, this is going to be the positive one. Okay. So I think we can apply. So this is at B, this is C, this is D. This is moment. We have this is the 5 kilonewton, and then we have all the distance. So this becomes. Let me change the color. This is 1 meter, and this is going to be 3 meter. And basically, like usual descriptions that we have done before, we take the equilibrium. We can take the sigma force for the y-axis equal 0. So we have Vb equal, or Vb plus 5 kilonewton equal 0. So Vb is negative 5 kilonewton. So this is very simple. And then the moment, let's say the moment, we take the moment at B equal 0, which means we are going to have, and then we decide this is going to be positive. So we have negative 5 multiplied with 1, and then plus 4, and then plus, don't forget the M at B. Okay. So MB will be 1 kilonewton meter. Okay, I think that is very, very, very clear, right? Very short, very clear. Maybe I will copy this to this part here. Now the second question is we have this distribution load or for the beam AC. And basically this is, I think, a little bit review of statics and the chapter 2 of the stresses. So first is we want to determine the reaction at A and C. So I think it's best to, I think maybe I will take the copy and I paste here. We take the free body diagram, right? So we have, since this is a roller, so we have only reaction at A for this one, and then reaction at C, and also in the x-axis, like that. And then we are going to compute the forces, okay? And as you may remember, how to compute the concentrated force from the distributed load, we can take this as a geometrical shape. Okay, we have rectangle and triangle, right? So we can take this rectangle, right? With the highest, or the height will be 40, and the side will be, the base will be 6. So for rectangle, this should be in middle, and multiply 40 with 60, so 240 concentrated force on the rectangle. And then you have the triangle, and then you can find also the area using the same height with the same base, 6, but then you need to multiply by 2 because of the triangle area. So half divided by 240 is 120 or 120. And then where do you put it? We need to put it, basically we need to divide by 3 the distance, and then we need to put the one on the having the on the left, right? The one having more distributed. Okay, so we are going to put here, and this is precisely, this is 2 feet, this is 4 feet. Okay. Okay, I think we have all the descriptions that we need to find the reaction at A. So finding the reaction at A, we can directly use the moment. Let's say using the A, that is the positive one. So we have 240, and then multiply with the 3 feet, right? This is 3. It's perfectly in the middle. So this is 3 plus 120, and 2 plus 6, it's 8. And then last one will be the cy. Cy will be counter, so negative cy, and then 12. We can compute the cy. This will be around 140 pounds. And do the same thing with the C. Well, actually, you can take the sigma F if you want, but let me just write with the sigma moment. So C will be AY 12, and then negative 240, uh, 3 and 6 is 9, and then negative 120, it's 4. AY is 220, or basically you can use the sigma Fy equals 0. AY plus CY equal 360. So AY is 220, right? The same. Yeah, I think we can just take the sigma force. And then the sigma force for x-axis, this will equal 0, so Cx will be 0. And then the second question, we need to determine expressions for the shear force and bending moment at the interval 0 to 6, which means between A, B, okay? Between point A and B. So what does it mean? So what we need to do, we are going to change this x according to the interval. Okay. For example, this x will be on between A, B. So then we can make it into our supposed to be. I think I need to copy again this part. Let me move to this slides here. Okay, so let me make this to here. Okay, so for x is between 0 to 6. Suppose that we still have this distributed loads, and then we have, this is the AY, which is 220 pounds, and then we have, this is X. So then with the concentrated load, this rectangle will have 40x, okay, for the loads, and the distance is x over 2. And then we have, this is V1 and M1. And suppose this is the name for this point is point A. And we can, first of all, we can find the V1. So we can take the sigma force for y-axis. So 220 minus 40x minus V1 equals 0. So V1 is 220 minus 40x pounds. Okay, this is for 0 until 6 feet. Okay, which means that the shear force will be in a linear equation. And based on if we change x, so the maximum is x is going to be 6. And then for the moment, we can take the moment at A equals 0, taking this positive. So 220x minus 40x and then x over 2. And then minus M1 equals 0. So M1 will be 220x minus 20 x squared. This is pound feet. And we have the quadratic equations for the moment. Okay. And then the third question is we need to determine expressions. So the same thing, but different interval. Okay. So different interval means that we need to take this interval, okay, the triangle. So this different distribution, different distributed loads, but the same procedures. So we take the same picture. Let me copy this again. And right here. So for 6 feet until 12 feet. And suppose that this is the C. So this is, we have 140 pounds for C, right? And suppose that this is, we cut this part. Okay. So this is this part. Okay. Cut this part, and we have a small triangle over here. And suppose this is small b, and then we have, here is, sorry, should be over there, V2 and M2. Okay. And taking the, perhaps the should be here. But since x is from 6 to 12, so x will be this way, right? 6 to 12, around. The whole thing is 12. So the thing is 12. So we can, to make our calculations easy, we can let this, all this line here up until here is the distance x, and this distance here we can use 12 minus x. Okay, I think much more possible. If we use another x, then this might contradict the, or have problem with the previous conditions. So because this is 12 minus x, then what we are doing here is we are going to apply the, this is half, okay, 12 minus x, that's the base, and then this will be 40 wait, I think to make it easy, we can look at this part here. If we take this as y, this is 40. This is a 12 minus x. And supposed to be y I think we have 12 minus x over 3. It should be 12 minus x over 3. So this one is y. So if we have a 12 minus x divided by 6, I think we can have maybe here, maybe here is 12 minus x. Maybe let that this 12 minus x is here and 6 over there. Y over 12 minus x is 40 over 6. So y is 40 over 6 multiplied with 12 minus x. This y is the same y with this. So the value for the concentrated force will be half 12 minus x, and then multiply with the 40 over 6, 12 minus x. Okay. So we have 40 over 12, and then 12 minus x squared. Okay. Okay, that's the force on this side. And this will be 12 minus x over 3. Right? And then what else do we need? Oh, here is 40 over 6. 40 over 6, 12 minus x. Okay, this side's here. Okay, I think we have cleared all the stuff. Taking sigma force for y. V2 plus 140 is equal 40 over 12, 12 minus x squared. So V2 will be in quadratic expressions. This is pound. And then for the moment, we can take the respect to B and take that as a positive rotations. So this will be M2 minus 140, 12 minus x. And then that part plus 40 over 12, 12 minus x squared, and then multiply with 12 minus x over 3. So you see that we have at least a cubic. Okay, we will get a cubic. So this will be M2 is 140, 12 minus x. And then I think we can solve this. So we can, I think, cancel this with 10 for 3, so 10 over 9. So this will be negative 10 over 9. 12 minus x cubed pound-feet. Okay, so that's basically what we've done. And basically, this is what will be the expectations. So you're going to see some equilibrium in beams, and you see that the first part from 0 to 6, from the rectangular distributed loads, you have the linear equation for the shear force, and then the second one, the moment is in the quadratic. So linear and then quadratic polynomial, right? This is for if you have the rectangular distribution load. If you have triangle, the shear force starts from quadratic, and then the moment is in a cubic. So you will see that for the shear force and the moment, their relations is going to be, the moment will be the integrations from the shear force. Okay? You will see that when we take the integrations, we are going to get the cubic. But we need to find how do we make sure that we are getting the correct result. And that is, I think, still in our content. So the expectations is you have the beam, and you need to compute those equations for the shear force and the moment, and then you are expecting to draw the graph. Okay? Draw the linear, quadratic, and the cubic. Okay? Okay, let me get to another introductions. How to relate all these loads, shear force, and the bending moment. Okay, this is just an example overview of the statics and some stresses that we have done before. Okay, if we look at here, some sign conventions for external loads on beam. we can have a positive distributed load. So let's say a positive, this is all positive. So positive means go up, okay, in the plus y direction. And then the positive is in the moment, this is also positive. Basically the right hand rule, okay? Because if we have the right hand rule, we have this, it's going to be outward, right? So using the right hand rule. Okay, now suppose we have this infinite small free body diagrams. Okay, so suppose that this is a small element, small pieces that we take. So we can take this in terms of, for example, the width will be the delta x. So this is infinite small free body diagrams. Okay. And we have the shear and moment, we say jump. Okay. Now we take the sigma force on y-axis. Then from the picture, we see that it will be Vx equal. We have the distributed load, the P of x, and then the delta x. So we have plus P of x delta x and let me introduce not 0, but this is O. I will tell you why and what is that. And then minus V this O is means of the order of, and delta P is going to be approximately closer to delta X, which means that this differences between the terms, if we divide by the delta X, this is actually like definition and limit, right? This is P of X plus O delta X. And basically, using the definition and limit, this could be taking as 0. We have dv dx is P of x. And then the same for the moment. We can take the sigma moment with respect to c and make it that as a positive directions. So this will be m of x, and then minus, if we look at here on the left part, we have minus m x plus delta x, and then the same with the, we have P of x and then multiply with delta x, and then multiply with the delta x over 2. So we write here plus P of x delta x over 2, this is squared, plus this is again, this is O. O will be basically eliminated after we solve this. and solve, and taking the delta x going to be 0, so ddx of the moment will be phi of x. And this is certainly what we are expecting. Okay, so the derivative of the moment will be the shear force, which I think we can conclude from our previous example that the equation that we get from the loads, if we derive the shear force, we get the loads. If we derive the moment, we get the shear force. And then if we take the sigma force for the shear, we could see that we get for shear jump, taking the y-axis as 0, VA minus, or maybe this minus is over there, minus VA minus plus delta VA plus P0, this is going to be 0. This is going to be this one here, okay? This VA minus. And then, since it will canceling, so delta VA will be P0. So what is VA minus? Minus means this is, since the point A is on the middle, VA is on the left to the point of the XA. And then we can also apply for this moment jump to get the sigma moment. So for moment jump, this is also we getting the same. So B minus, which means on the left of B a little bit, minus plus delta MB, and then minus M0. So delta MB will be equal to the negative MB, or M0, sorry. So we can integrate the equation. For example, here we have the dv dx here. We can integrate this and then basically evaluate from x1 to x2. And we are expecting to get this v2 and v1, okay, which is basically, this is integration for vx dx. And then the same way for the v, we are going to get this vx dx. So this is the conclusions. Which we are going to observe in the later expressions. The more general versions, we can apply the Vx and Mx. Is basically V1 plus additional, or if this is a variable, this will be P, and let's say it be psi, just another variable, or you can change with T as well, maybe change with T. Okay, and basically this can be expressed in more general term. Okay, I think we can have another example and expectations for solving the equilibriums. Hopefully that will be completed tomorrow. So tomorrow will be no quiz. Quiz will be 28. So I will have completions now, tomorrow, and also the Monday class. Okay.